What if you could run C++, Rust, or Python inside a web browser at near-native speed? Or what if that same binary ran on a server, a Raspberry Pi, or the edge of a CDN without any changes? That's WebAssembly. And it's become much more than a browser trick. Hey, welcome to AmtocSoft. I'm going to break down WebAssembly, what it actually is, how it works under the hood, and most importantly, why it's now being used far outside the browser in production servers, edge runtimes, and even embedded systems. By the end of this video, you'll understand why Figma, Photoshop, and Shopify all bet on WASM, why the WASI standard changes everything for server-side compute, and when you'd actually reach for WebAssembly over JavaScript or a Docker container. WebAssembly is a binary instruction format designed to run at near-native speed in a sandboxed environment. It's not a language you write, it's a compilation target. You write code in Rust, C, C++, Go, or even Python, and your compiler outputs a .wasm file. That binary is compact and portable. A WebAssembly runtime handles memory safety and sandboxing. WASM code can't access anything it isn't explicitly given access to, making it extremely safe by default. The browser engines, V8, SpiderMonkey, WebKit, all ship a WASM runtime, so a WASM binary you compile once runs in Chrome, Firefox, and Safari without changes. Performance-wise, WASM typically runs at 70 to 90% of native speed, far faster than JavaScript for compute-intensive tasks. Figma measured a 3x speedup over their previous JavaScript renderer after migrating their core rendering engine to WebAssembly compiled from C++. Here's where it gets genuinely interesting. The browser is just one runtime for WebAssembly. Once you compile to .wasm, that binary is portable. It can run anywhere a WASM runtime exists. WASI, the WebAssembly system interface, is the standard that made this possible outside the browser. WASI defines how a WASM module accesses system resources, files, sockets, clocks, and environment variables. Think of it as POSIX for WASM, a minimal, capability-based interface to the operating system. With WASI, a Rust function compiled to .wasm can run in WASM time as a standalone server process, in Fastly's Compute or Cloudflare Workers as an edge function, in Fermien's Spin framework as a microservice, or in any IoT runtime that supports the spec. Solomon Hykes, who created Docker, said, "If WebAssembly and WASI had existed in 2008, we would not have needed to create Docker." That's the scope of what WASI enables: portable, sandboxed compute without containers. Let's talk about who's actually using this in production. Figma compiled their multiplayer design engine from C++ to WebAssembly and saw a 3x performance improvement. Their team has said it's impossible to achieve the same result in pure JavaScript. Adobe Photoshop on the web runs core, filters, and compositing via a 1.2 GB WebAssembly module. The same C++ code that ran on desktop for 30 years now runs in your browser tab. Shopify uses WebAssembly for their checkout extensions, untrusted merchant code that runs securely in the Shopify storefront without being able to exfiltrate data or crash the host page. Fastly and Cloudflare both run customer edge logic as WASM modules. Your code deploys globally across hundreds of points of presence in seconds, with cold starts under 1 millisecond. And in the AI space, runtimes like Llama, CPP are experimenting with WASM targets to run quantized models on any device that has a WASM runtime. Under the hood, a WebAssembly runtime parses the binary, validates it against the spec, then JIT compiles it to native machine code for your CPU architecture. Modern WASM JITs are so fast that a cold start, loading, and compiling a WASM module takes under a millisecond for most modules. Memory isolation is built into the spec. Each WASM instance gets a linear memory region and cannot access memory outside it. There are no raw pointers, no buffer overflows past the sandbox boundary. This is why Shopify can safely run untrusted merchant code. The component model, finalized in 2024, goes further. It defines how WASM modules interact with each other using typed interfaces, enabling polyglot microservices where a Rust module calls a Go module without a network hop. So when should you actually use WebAssembly? Versus JavaScript. Reach for WASM when you need CPU-intensive compute, image processing, video codecs, physics simulations, cryptography. For UI logic and DOM manipulation, JavaScript is still the right tool. Versus Docker containers. WASM modules are 10 to 100 times smaller than container images, start in under a millisecond versus Docker's seconds, and share no operating system surface area. The trade-off is that WASM can't run arbitrary Linux processes, yet WASI is still maturing. The sweet spot today is edge functions where startup time and binary size matter, plug-in systems where you need safe, untrusted code execution, and cross-platform libraries you want to compile once and run everywhere. The WASM ecosystem is moving fast. 3 things to watch. The component model, the finalized spec for typed, composable WASM modules, lets you build polyglot systems where a Python module calls a Rust module calls a Go module, all sharing memory-safe typed interfaces. WASI 0.2, released in 2024, added sockets support, making WASM viable for any networked workload. And WASM Cloud is an open-source platform treating WASM components like distributed actors, scale them across any cloud, any edge, any device without changing the binary. The trajectory is clear. WebAssembly is becoming the universal compute unit for the next decade. Not just browsers, not just edge. Everywhere compute needs to be portable, safe, and fast. Quick recap. WebAssembly is a portable binary format that compiles from any language and runs at near-native speed in a safe sandbox. WASI takes it beyond the browser to servers, edge, and embedded. Companies like Figma, Adobe, and Shopify are running it in production today, and the component model is making it the foundation of the next generation of distributed systems. If this clicked for you, subscribe. I publish videos like this every week. Next up, we're covering Cloud 3 architecture, hybrid, multi-cloud, and sovereign infrastructure, and what it means for how you build. Buy Me a Coffee link is in the description if you want to support the channel. See you in the next one.